Good morning, friends. This is once again Dr. Kushal Bhattacharya. Now I today continue the second part of fracture mechanics, which is solving fracture mechanics or treating fracture mechanics in respect of stress intensity approach. Previously, we have studied fracture mechanics in the respect of energy based approach, where Griffith's criteria and Irwin's corrections are there. I haven't gone very details on that. Whatever required for your syllabus, graduate level syllabus, I've discussed that part only. Now today I should be discussing the stress intensity approach of, or the stress based approach of treating fracture mechanics problem. So it starts like this. See the stress intensity approach. Now you could see a figure is given. A figure is given on this. A figure is given. You could see a figure. Now the figure represents stress distribution of an element near the crack tip of a crack in an elastic material. So the material is basically linear elastic material, and over there forces are applied in both direction. Over here the forces are applied in both direction. So if forces are remote forces, if remote forces are applied in both directions, then the tip of the crack, what is the stress scenario at the tip of the crack is shown over there. Obviously the stress distribution is in plane, that is the plane of the board. It's not perpendicular to the board, that is it is showing only x-axis and y-axis. So if you see the coordinate system, it is showing only x-axis and y-axis, that is the perpendicular to the board, that is z-axis is not shown. So an elastic material, linear elastic material under stress condition in the crack tip of the element, an element in the crack tip, what is the stress distribution? It is shown. You could see the direct stresses sigma xx on both directions, sigma yy on both direction, and tau yx and tau xy, the shear stress component in all the directions. So this is basically all the stresses are shown over here. Now the first thing is that what we have to consider is that each what are the thing it resembles is that each stress component is proportional. You could see it's now if you want to find out what is the value of the stress, so the value of the stresses is given in this format. Sigma xs is given as k1 by 2 pi r cos theta 2 into 1 minus sin theta 2 into sin 3 theta 2 by 2. Now what is this theta? Theta is this angle of the element. The theta is the stress distribution, that is r, when you are calculating the stress at a distance r and at an angle theta, So from this you could see that sigma xx can be calculated as k1 root 2 pi r into cos theta by 2 into 1 minus sin theta by 2 into sin 3 theta by 2. Sigma yy is also given as k1 by root 2 pi r cos theta by 2 into 1 plus sin theta by 2 into sin 3 theta by 2, and tau xy, or tau xy and yx are both same. So now this is the this is called the tau xy and yx are both the same in the opposite directions. So it is written as k1 by root 2 pi r into cos theta by 2 sin theta by 2 into cos 3 theta by 2. Now the important study of this is that we could see that each stress component is proportional to a single constant k1. So every stress component you see, there is a single constant k1. If this constant is known, the entire for that perfect material, for that perfect linear elastic material, if this constant is known for that perfect linear elastic material, the entire stress distribution at the crack tip can be computed with the equations given. So with the help of this equation, if this constant k is known, we could calculate the entire stress distribution. Now this constant, what is this constant? Basically this constant is known as the stress intensity factor. This constant is known as the stress intensity factor, which completely characterize the crack tip condition in a linear elastic material. As because if we know the value of k, we could calculate the sigma xx, sigma yy and sigma xy. So both, all the stresses are known to us. Only the unknown, because we could calculate the theta, from where we are getting the value of the stress, and what is the distance at which we are calculating the stress. So r, theta and r unknown. So only if k is known to us for that material, we could easily calculate the stress distribution. So that constant is known as the stress intensity factor, which completely characterize the crack tip condition in a linear elastic material. Okay. Now, if a material fails locally at some critical combination of stress and strain, so what happened if the crack progresses? When the crack progresses, suppose if the crack moves like this, if the crack progresses, what happens? So that is the material fails. That indicates the material fails. So if a material fails at some critical condition of stress and strain, because as we go on increasing the stress, we go on increasing this value of stress. If we go on increasing this value of stress, that is the remote stress. If we go on increasing this value of this remote stress, what happened? The value of this will increase, and the material could not able to sustain the load, and a new surface is formed. And the crack grows. So if a material fails at some critical condition of stress and strain, then it follows that fracture must occur at critical stress intensity factor K1C. This K1C is an alternative measure of fracture toughness. So this K1C is a material property, because if the material, if K1, now what is if the material becomes, suppose this is the equation for stress intensity factor, which is known as K1 into sigma into root pi a. Now if we go on increasing the value of stress, what happens? At a certain, then the crack will progress, then at a certain value of stress, and at a certain critical crack length limit AC, what happened? The material will fail. So that point is called as the K1C. So K1C can be treated as the property of the material. Now, as we have discussed that K1 is equals to sigma root pi a. Now K1 is equals to sigma root pi a. If you recall the figure of a of an infinite plate, consists of a crack length of twice a and the thickness b, and sigma is the remote stress. So from there you could find out the value of this K1 is equals to sigma root pi a. That is basically the proportional to the stress and the crack length, that is the twice crack length, and this is proportional to crack length. Now failure occurs. When failure occurs? When K1 is equals to Kc. Then when failure occurs, then K1 becomes equals to Kc, then sigma f is the fracture as a failure stress, and AC is the critical crack length. That means when you go on increasing the remote load, so then the stress will increase, and ultimately at a value of sigma is equal to sigma f, what happens? Fracture occurs, and when the crack length is AC, critical crack length. So that is called the that K1C is called the property of the material, or the stress, that property is called the stress intensity factor of the material. So if K1 is considered, as a driving force, if K1 is considered as the driving force for fracture to occur, then K1C is a measure, of material resistance. Then K1C is basically a measure of the material resistance offered in order to resist fracture. So, and that is particularly for the same material, that is particularly fixed for a fixed material. For material A, K1C is fixed. For material B, K1C is fixed. So what happens? That is a material property. That what I want to say is that K1C is basically a material property, because it is up to that limit of K1C of K1 that it could resist. Then if you come to the value of K1C, what happens? Fracture will take place. So that is the material property. So K1C is considered as a material property. Now as G1C, K1C is also assumed to be size independent. As because it is a property, then it is have to be a size independent material property. So now if you compare the energy, now if you compare this to the above two equations, you would see from the energy based equation, we say that G is equals to pi sigma square A by E, where pi sigma square A by E, where G is the driving force for the crack, where G is the driving force of the crack. Now when G comes to about GC, that is again pi sigma F square into AC by E, fracture occurs. Similarly, when K becomes equals to K1C, that is sigma F into pi AC, fracture occurs. So that indicates that the energy approach and stress intensity approach to fracture mechanics essentially equivalent for linear elastic material. Now you know what is called linear elastic material. That is the material which is very much sharp. That is which the material that we have shown before also. The linear elastic material is basically like this. The linear elastic material is like this. That is if you give pump some energy to the system and you reduce the energy to the system, it will come back in the same manner. And linear elastic means the curve is linear. That is stress is proportional to strain. Okay, so that is all about the fracture mechanics, the very introductory part of fracture mechanics. So if you like my lecture, please put a thumb up to it and subscribe to my channel for more and more lectures. Thank you. Have a good day.